Oh, welcome to my laboratory, and today I will be discussing intersample peaks. Probably thinking, well, what in God's name is an intersample peak? Well, an intersample peak are these nasty little things that overshoot past the 0 decibel ceiling. And as you can imagine, if anything passes this ceiling, it causes distortion. And as we know, other than the sometimes very useful audio effect, distortions across a whole mix, for example, is extremely undesirable. And as a little tidbit here, these distortions are almost negligible, but you have to think that this is happening at such a fast rate, thousands of times a second, that you sort of have an overall distortion profile associated with a mix when you have too many of these overshoots. So as you can imagine, you don't necessarily want this happening in your mix or your song. And well, you might be asking, well, how do I get rid of these things? Before we can jump directly into that, we must first go over the digital representation of analog. Here is a graph of amplitude as a function of time of a sound. So as you can see here, this is a sine wave, and it has a specific frequency associated with it. It has a specific amplitude associated with it. And one thing to notice is that this analog signal is continuous. There's no gaps in between this line, okay? This is just a full continuous signal. One of the key differences between analog and digital is that analog is continuous, where digital is not. Now, the way digital represents an analog signal is through samples. Most consumer music runs at 44.1 thousand hertz. What this means is that the analog signal is being sampled 44.1 thousand times per second. So what does this mean? Well, it means that every 44.1 thousand times a second, there is a sample being taken of this analog signal represented here. So these little circles are snapshots of the amplitude of this signal and its frequency information associated with that at a given time. So that later, when you no longer have this continuous signal, the computer can then rebuild that wave based upon the sample information. So as you can see, the computer can somewhat connect the dots and recreate that waveform. Now, to connect these two ideas of what is this digital representation of analog and an intersample peak, what do these two ideas have to do with each other? Well, let's think about the operation of a limiter. So the function of a limiter is to attenuate a signal when it passes a certain threshold. So normally we set that to 0. Anything that passes 0 gets attenuated back down to 0. This is a critical understanding point right here. That limiter is functioning on a specific sample rate. The limiter is functioning at these many samples per second. Now you have to ask yourself, what happens when you have a signal that is actually higher than, let's say here is 0 dB. You have to ask yourself, well, what happens when we have a signal that's higher than 0 dB, but the limiter is not measuring that peak at that moment, okay? And the reason why it's not measuring at that moment is because the resolution is not fine enough. It's outside of that sample rate. This peak is occurring in between these two samples, okay? So that is what an intersample peak is. The limiter is not catching these peaks because the resolution of the sample rate is not fine enough to catch these peaks that are occurring in between the samples. So really, that's the idea. It's when, any plugin, like any compressor, any digital thing is operating at this specific sample rate. And sometimes you're going to get these peaks that are occurring in between these sample times. Like here, for example, here, well, it caught that because, well, it measured it on the peak. And here, oh, caught that because it was happened to be measuring on the peak. Well, here, well, it wasn't measuring on the peak. And, you know, that's when we convert that to MP3 or we just play it out on, you know, a consumer system. Well, this is going to clip. This is the clipping. This is causing distortions, and this is what we don't want. So now that, you know, we kind of understand what the intersample peaks are on a more, you know, technical understanding, you have to ask yourself, well, how do I measure the damn things? You know, like, how do I know what's going on? Well, it sucks because there's not a lot of tools available for you to actually measure intersample peaks. Pro-L is extremely good limiter because, well, look at this right here. Have you ever wondered what that means right there? That IS, it's a little blurry, but it says ISP. It means intersample peak detection. Boom, turn that on, right? A little, a bit of a mix playing here. So now I'm gonna turn intersample peaks on right now. Boom. Now I want you to look right here. Those are the measurements of these overshoots. These overshoots right here, this is showing you the amplitude of these overshoots. Probably like, well, shit, like that sucks. And this is actually a product of, if you limit it more, you actually end up getting, you know, generally more of these overshoots. Okay, so now you're gonna ask, well, how do I, you know, mitigate this problem? Well, you have to be running at a higher sample rate. So if you look right here, oversampling, I'm gonna turn that 4 times. What that's doing, that's taking 44.1 thousand hertz and multiplying this operational frequency by 4 times this. So it's making it 4 times more fine and smooth. So now that I have my oversampling on, I'll refresh my meter. Now I'm getting very small overshoots. Like these are far more workable than 1-2 dB of overshoots. And you know, I wish I could say that there's more tools to mitigate these overshoots, but there really isn't a lot. And you know, the quality of your limiter is, you know, going to have features like oversampling or intersample peak detection. And really, you know, the main thing to take away here is just to know what these things are. This is my strategy to deal with intersample peaks. But in general, you just have to be aware of, you know, what it is. And yeah, well, hope this helps you.